Okay, so let's continue the class of application of derivatives. We have earlier talked about multiple concepts. For just a quick recap, let me revise all the concepts that we have discussed earlier. Okay, so okay, so let's discuss here. We were discussing about applications of derivative. As you know, the name suggests that we are going to look in the application, the use cases of derivative. We've discussed about how speed, acceleration, and we can relate these two things and we can find out their relation and their rate of change with respect to each other. Okay. And after that, we have also discussed about functions. As we know, every function having two variables, y and x, or any two variables, can be represented on the 2D graph. So the function will be having some curve, some straight line, or some other field. So basically, function like maybe let's say this is a function. So while finding the tangent of the function, what is tangent? At any point that how the derivative, when we find the derivative of the function at that particular point, we basically find out the rate of change of function. So there we can find out the rate of change of function, like the rate of change of y with respect to rate of change of x. So that is basically derivative. That's basically the function. So functions are of two types: increasing function and decreasing function. So increasing function is like, let's say there are two values of x, x1 and x2. Let us say x1 is greater than x2. And increasing function says that when we increase the input in a function, like let's say f of x is a function, like y is f of x, and y is a function of x. So if we increase the input, that is x, in the function, the y, the function's value output also increases. Then it is known as the increasing function. Or it may remain the same also. So if we are increasing the input, it may increase or remain the same. This is termed as increasing function. Talking about decreasing function, let us say there are two variables and x1 is greater than x2. This time, on increasing the input, the function's value will decrease or will remain the same. This is known as increasing and decreasing function. So we were discussing about the monotonicity of functions, or let us use a simple term, strictly increasing function and strictly decreasing function. Sorry for the background noise. So strictly increasing function says there are two variables x1 and x2, x1 and x2. x1 is greater than x2, x1 is greater than x2. So the f of x1, the when we increase the input, it must be greater than the output given by x2. And now when we are increasing, like the when the input is increased, so the value function decrease for sure. So that is called as strictly increasing and strictly decreasing function. How we can particularly check whether a function is strictly increasing or not? We can basically check at any point by taking its derivative, but we can only check on by taking derivative on a for a particular point. Okay, we cannot check for a whole period. We will be discussing about how to do that later. So f dash of x, if it is a strictly increasing function, slope is going to be positive, because if there is a function and if it is increasing, like in this phase from the here to here, function is increasing, the slope is going to be positive. For strictly decreasing function, f of dash is going to be less than 0, which is it is going to be negative. Okay, so f of dash of x is what? As we have discussed it earlier, dy by dx basically. So in the previous slide, if we discuss about increasing function, then f of dash of x should be greater than 0 or equal to 0. Okay? F of dash of x can be less than 0 or should be or can be equal to 0 in a decreasing function. For strict equation, for the strict functions, we are having the condition of only inequality, not in equality condition is not included in this. Okay, so this is about strictly increasing and decreasing functions. And later on, we also talked about functions having maxima and minima, local maxima and local minima. So let me draw a simple figure for you. So let's say that this is a y-axis representing as y is a f of x. This is x-axis. Okay. So let us draw a graph. Say, uh, let's draw like this. Okay. So let us, for reference, I'm drawing a line, simple line. Okay. So here you can see there are like multiple periods. So let us name those periods. And let us say this is A, this is point is B, this point is C, this point is D, this point is E, this point is F. Now, for specifically talking about period A and B, what is the maximum where the function is getting its maximum value? So it is this point, right? So let us call it as it's an extreme point, so we can it is known as extreme point, critical point. Okay, where f dash of x is basically 0. So we'll discuss about it later on. First, let us understand that for this value of x, the function is having some great peak. For particular period of b and c, lowest peak is here. It is x2. Let's name this x3. Let's name this x4. Let's name this x5. So if we talk about basically A to B open interval, what is the maximum point? Where is the maximum, where the function is maximum? Locally maximum for A and B, x1. And if we talk about basically from period A to F, where the function is maximum, it is on x1. Let's talk about period B to C, where the function is minimum. The function is minimum at x2. And let's talk about C and D. The function is maximum at x3 in C and D. Otherwise, it is maximum at x1. For D and E, the function is minimum at x4. For E and F, the function is locally maximum. For this particular period only, the function is locally maximum on x5. So what we can see here, that this particular point, this is the highest peak of this function, is known as absolute maxima. And the very low peak, the very low peak of this function, which is what? Which is this very lowest of the function is absolutely minima. Okay, that's why we know call it as absolute minima. And when we talk about local period from C to D, it is a local maxima. It is a local minima for D and E period. And same for this also. This is local X maxima for E and F period. So I hope you're able to understand what is like maximum and what is minimum. So let us talk about local maxima and local minima a little bit more by giving its definition. Okay. So let's draw a graph first. Let us say this is a curve of the function, and let's call some variables that this is, let's name this point. This point is A point, and this is B point, and this particular point height is C point. So what is local maxima? As you know from the graph, you can see like the local maxima exist at x is equals to c. So f of c is greater every time it is greater. Every time it is greater for all values of f of x, where x belongs to a and b. So this is what known as local maxima, where a and b are also included, depends on the function. So on f of c, the function's value is just the maximum. Like uh, here, the value of f of x is going to be maximum. Yes, if we are taking a, like c is existing in this period, so we have to do equality sign for x being equal to c, because c is also lying in this period. Okay, so this is basically what local maxima is defined like in bookish and in definition. So where f of c is greater than f of x for all x belonging in this period, where at c, as you can see, if we take the tangent of this, so the tangent angle is making an angle with the x-axis of what? Of 0 degree. So basically the slope, so the differentiation f dash of c is 0. Okay, this is how local maxima is defined. Let me use some of my painting skills. Yeah. So going further, let's discuss some more concepts about, as we have discussed earlier, local maxima. So same goes for local minima, exactly the same. So let's just copy the slide and make changes to it. Okay. So let's change this name. And rotate this graph, because we are going to discuss about minima grade. So, and also also this will be changed. So now we are going to discuss about local minima. So as you can see from the graph, at C, local minima exist. C. Okay. C, you can see local minima is there locally. Why we are using local word? Because we are discussing about local period. We don't know about the whole graph. If we are discussing about a whole graph, then we'll use absolute here. So here we can see for all f of x, f of c is the least. So the inequality sign would be changed. Okay. So here for all f of x belonging in this period, f of c is gonna be very less than all of them, except for c. Is going to be equal. For f of c will be equal to f of c. Yes, that's very much self-explanatory. So this is about local minima, where we are discussing about this function's curve from A to B. C is the point where the minimum value exists. And here also you can see if you draw a tangent, so its angle with the x-axis is what? 0. And tan of 0 is what? 0. That's why our slope is also 0. So we can write the derivative is also 0. And C is basically known as critical point. Okay, critical point. So we have discussed about local maximum, local minima. So basically, let's revise. As we were doing recap, so let's discuss one more thing. Let's discuss about the how we can calculate, or how we can know that this but on this particular point or in this particular period, there is a local maxima or local minima. So there are two tests for this. First test is first derivative test. As we were discussing about slopes earlier, if like there will be any function, if there is any function, background pressure. If there is any function like decreasing, so if we will be discussing about its, let's say that we know this is a critical point. Okay, so this is a critical point. So the like derivative, let's discuss about its uh, tangent. So on particularly this, on this point, the tangent would be zero. This tangent would be zero. On particularly this point, tangent would be negative. The slope of the tangent would be negative. And the point which is like ahead there, ahead then this critical point, and on this particular point, the slope of the tangent would be positive because it would be making a, 0 to 90-degree angle with the positive x-axis. So that's why like 10, you know about the property of 10. Here it is positive, and oh, after school, here sign will be positive. Here all trigonometric function will be positive. Here 10 will be positive in third quadrant. What is this? 0, pi by 2, pi, 3 pi by 2. And here cos would be positive. Here as sine is positive, so cosec will be also positive. Here cot will be also positive. Here sec also would be positive. So you can remember this trick by remembering the all, after school to college. A stands for all trigonometric function. S stands for sine. Uh, T stands for tan of theta, and C stands for cos of theta. I hope you are able to understand it. So that's why the sign of this tangents here, the sign of slope of the tangents would be minus before the critical point, and after the critical point, it would be positive. On the critical point, as you know, would be zero. So, and this is the case where we are able to see that this is a local minima. So, for local minima, we are discussing about the sign of f of dash x. On C, it would be 0. Between C and minus infinity, it would be negative. Okay, it would be negative. And between C and positive infinity, it would be positive. So like if the graph is some graph is having negative slope, so it would be going something like this, and on C it will become parallel to the x-axis, and then if it is having some positive slope, then it would be going upwards. So this is how you can also remember that this is a case of local minima. Let me again use my painting skills. Very good skills. Oh, not a problem. We can have this page also. So moving ahead, discussing about like local maxima. So in this case only, we can understand that first let me, okay. So let's make this diagram a little bit small so that we can discuss the case of local maxima also. This is about local minima. Discussing about local maxima, discussing about local maxima, drawing the graph of function. And here, as you can see from the picture itself that like on the point C, so the slope is just parallel to the x-axis, and so let's draw tangents here. So drawing tangent just before C, it would be making some angle which would be from 0 to 90 degree to the positive x-axis. So, and it would be making some angle between 90 to 180 degrees if we go ahead then the C. Okay, so this is having positive slope, this is having negative slope. So minus infinity to plus infinity. If we talk about local maxima, we talk about local maxima and sine of f dash of x, the slope. Before C, it was positive. After C, it was negative. So the graph would be somewhat like this because the slope is positive. On C, it would be parallel, and then on negative, it will start decreasing. So this is the case of local maxima. So I hope you are able to understand. So first derivative test complete. Let's discuss about second derivative test. Second derivative test is used when the first derivative test is failed. Or you can also directly use this second derivative test. When first derivative test fails, it means that the value here is 0, or both the signs are negative negative, both the signs of f of dash of x are positive positive. So in that particular case you will not be able to decide. So in that case you can also use second derivative test. So what second derivative test is very simple, that you have some function and you have to discuss its maximum or minima at some point at x is equals to c. So first of all, we have some function, basically that's it, and then you will derivate this function f of dash of x, and then you have to equate this function to 0, and for f of dash of x will be 0 for x is equals to c, and that point will be known as critical point, and critical point can be more than one also. So after that you will differentiate this function further. Let me rewrite and restructure it in better way. So your first step, if you have some function, your first step would be to derivate it. And then second step would be f of dash of x, you will have to equate it to 0, and there will be some x values, and they will be known as critical point. They can be more than one also. Okay. Then further differentiate it again with respect to x, f of dash of x. Now what you do, now put c's, these were known as extreme or critical points, basically where a slope of the function at that particular point is 0, is parallel to the positive x-axis. So you have this function now. Substitute x with critical points. If critical on this particular critical point, f double dash of c1 and f dash of, after substituting x for c1, and if it comes out to be negative, then function is having local maxima at that point. If for some value of critical point it is positive, then function is having minima at that point. If in case it equals to 0, then the test fails, and you have to use and go back to first derivative test. So remember this is very very important, and this is basically ulta, this is reversed, so you can use reverse analogy to remind this. So that's about first derivative test and second derivative test. So if I'm like recapping all the classes, let me also teach something about straight lines. Okay, so basically straight lines are like have a linear function. Linear function is what? The function which is having degree 1. Okay. So, and the basic representation of the equation of line can be like if you have a intercept on y-axis of line and you have slope, then you can make the equation of line in this form: y is equals to mx plus c. Okay. And what is what? Let me explain. Let's say this is a graph. Let us say this is the graph, and this is our straight line where basically this point is known to us. That is, like, if this is x-axis, this is y-axis. So x would be 0 here, and there will be some intercept here. And also, you know what is the slope. Slope is also known as u. This is represented by m. So basically, y and x would be remaining like they are here. They are variables. Y and x will also be there, but m and c will be substituted with these values if you have. And if you have like 2 points of straight line, then you yourself can find out the slope. Slope would be change in y-axis, change in y, on change in x. So basically, from the previous equation of straight line only, we can write it as into x, and you do not need to we do not need intercept here in this case. Okay. So this is how you can write the equation of straight line, and we will discuss more in straight line chapters further. So now you have to understand one point about tangent and normal of function. Okay, you know, like every function would be having some curve. Every function would be having some curve. It can be in any form. Okay, doesn't matter. But on every point, we can find out its derivative, basically rate of change, and that is what? That is slope. And that is slope. Yes. So what is a tangent? What is a tangent then? A tangent is a, like, on any particular point, it touches on a single point nearby. Okay. So drawing tangent would be something like this, that it touches only once. Okay. So this is like a tangent, which is touching it only for once. Now, for the equation of the straight line, and basically what is a tangent? This, from this, we can see that this is a straight line. So for the equation of the straight line, what will be required will be its slope. Yes, and if we know somehow one point on this, like a single point on this, so we can also write its equation. So basically, this is a tangent is a straight line, and we can find out its slope. How? We can find out, like, we can project this further by using this theta. Slope would be m tan theta. Okay. And now, for finding out the equation of this particular tangent, listen to me carefully because it is very important. So, equation of tangent. Okay. So basically, we know about the slope, and also about this point, this particular point, which we are discussing about. So this would be x and f of x, right? So we have one point here, and we have the slope also. So y minus y1, sorry, here we have written f of x. Y minus f of x upon x minus x1. Let's write it as x1, also this one x1. Okay, you can equate this to m, and now simply this will give you the equation of tangent. Great. How tangent can, how the slope m, how the slope can you find out? It can be find out by tan theta, and also because it is a given function and it is somewhat lying on this particular point. So when you will differentiate the function dy by dx or d of f of x by dx, then you can have the slope, and you already have one point on this particular point. So basically you can find out the equation of tangent using this. Let me simplify it and rewrite it. For equation of straight line, you need 2 points. No, you need two things. One is slope here, and second is a point. So you slope you can find out by differentiating the function, and your point you can just put the value of x in this function. You can find out that easily. Okay, so let us say x1, this is the point. So the equation of tangent, because tangent is a straight line, y minus f of x1 upon x minus x1 would be equal to dy by dx. Don't cram this, just understand this. Okay, how have I find out? So this is about tangent. And what is a normal? In the same course, we can understand a normal is basically a straight line passing through the tangent point perpendicularly. It is basically perpendicular to the tangent always. Normal is always perpendicular to tangent. This is normal and this is tangent. Okay, so now we know from a property of straight line that if two lines are perpendicular, and if this line correct, uh, hmm, perfect. So if this is a straight line, this is another straight line. If this particular straight line has slope m1, if this straight line has a slope m2, and these are perpendicular, so the slopes multiple is going to be -1. Their product is going to be -1. If there are two straight lines which are parallel, so their slope would be simply equal. This is one case. This is another case. Perpendicular straight line. These are parallel straight lines. Okay, parallel straight lines. So good. So as we were discussing about the slope of tangent, it was dy by dx. So the slope of normal would be we can understand it from here, -1 by the slope of tangent. So dy by dx. So simplifying it, we can write it as this. These are two important things. You can remember these. So this is about the recap. We have only discussed about those things which we have discussed earlier. Okay. So you can watch this session and revise like whole of application of derivative. Okay, thank you.